It's funny, isn't it? We look up, we see a helicopter zipping across the sky, and it almost seems simple. Like, oh, it's just going up and down.
Yeah, you'd think so, wouldn't you?
But when you really start digging into it, the whole idea of achieving flight with rotating blades, it's just mind-bogglingly complex and really a testament to human ingenuity.
It absolutely is. There's so much more going on beneath the surface than meets the eye. It's not just about going up and down. It's a whole different way of thinking about flight.
So today we're going deep, really deep into the world of helicopters. We've got some seriously fascinating technical documents that we've been poring over,
Oh, yeah. We've been digging into the nitty-gritty.
and we're going to try to distill all of that, the really complex stuff, into something that's a bit more digestible. Because we want to understand what makes these incredible machines tick, how they came to be, how they work, why they're so important.
And why they're so cool. I mean, come on. Who doesn't love a good helicopter?
Exactly. So let's get right to it. First things first, what exactly is a helicopter? I mean, yeah, we all know what they look like. Those whirling blades are kind of a giveaway. But what actually sets them apart from, say, an airplane? It's the defining characteristic.
It all boils down to how they generate lift. Unlike airplanes, which need to move forward to create lift over their wings, helicopters generate lift directly upward using those spinning blades we call rotors. That's why we classify them as rotorcraft or rotary wing aircraft.
Rotorcraft. I like that. Very descriptive. And speaking of descriptive, the word helicopter itself has a pretty interesting story behind it, doesn't it?
It does. The term helicopter was coined in 1861 by Gustave de Ponton-d'Amécourt. And he didn't just pull it out of thin air, he combined the Greek words for spiral, helix, or helikos, with the word for wing, turon. So essentially it means turning wing.
Turning wing, it's so apt.
hmm
But it wasn't until much later that the turning wing truly took flight. So let's rewind a bit. What makes helicopters so special? Why are they such valuable assets in so many different fields?
Those turning wings, the rotors, are the key. They give helicopters some pretty incredible capabilities. I'd say the biggest one is their ability to take off and land vertically, what we call VTOL. Since they don't need a runway to get airborne, they can operate in all sorts of environments that would be impossible for fixed-wing aircraft.
Yeah, like think about those search and rescue operations in mountainous terrain, or landing on a ship at sea.
hmm
You can't exactly land a 747 on a mountaintop, right?
Exactly. And that's not even mentioning the ability to hover, to basically stay put in the air. Imagine trying to do that in an airplane.
It's clear these machines are incredibly versatile, but I bet piloting them is no walk in the park.
Oh, you're absolutely right. Piloting a helicopter is incredibly demanding. It takes a lot of specialized training. You're not just steering, you're managing lift, thrust, yaw. It's a constant balancing act, and you're doing all of this while thinking in 3 dimensions.
Yeah, you're not just dealing with left and right, forward and back. You've got that vertical axis to think about too.
Precisely. And that means using all your limbs in coordination. Your hands are on the cyclic and collective, your feet are on the pedals, and everything needs to work together seamlessly.
So these aren't your average Sunday drive machines, that's for sure. But let's get back to the history of helicopters. As with most technologies, I'm assuming the path to today's sophisticated machines was a bit bumpy. When did we first see helicopters that actually worked reliably?
Well, there were a lot of early attempts, and some even saw limited production in the early 20th century. But it wasn't until 1942 that a truly production-ready helicopter emerged, and that was Igor Sikorsky's VS-300. It was the first to feature a single main rotor and a tail rotor for anti-torque control. And that basic design became the industry standard.
So Sikorsky really cracked the code, huh?
In many ways, he did. In our source material, you can actually see a diagram of the VS-300 in figure 1 to 5. And if you look closely, you'll notice that single main rotor, tail rotor configuration we see on most helicopters today. But things didn't stop there. There was another major leap forward with the arrival of the turbine age.
The turbine age. Sounds intriguing. Tell me more.
Well, in 1951, Charles H. Kamin outfitted his K-225 helicopter with a turboshaft engine, making it the world's first turbine-powered helicopter. Then, a modified Navy HTK-1, also by Kamin, became the first twin-turbine helicopter in 1954. It wasn't until the Sud Aviation Alouette II, however, that a turbine-powered helicopter went into mass production.
Turbine engines must have been a game changer. What were the big advantages they offered?
Oh, they were huge. They're much more powerful for their weight compared to the piston engines used before, and they produce far less vibration, which makes for a smoother ride and puts less stress on the helicopter's structure.
Plus, I'd imagine they're more reliable and easier to maintain.
You got it. Now, we mentioned search and rescue earlier, but helicopters are used in a ton of different roles, right?
Absolutely. Their versatility is one of their most remarkable qualities. We've got a great illustration in our source material, Figure 1.3, that shows just how diverse their applications are. We see them in construction, lifting and placing heavy materials, and of course, firefighting, where they can deliver water or retardant with incredible precision.
And let's not forget transportation. Whether it's ferrying passengers or cargo to remote locations, helicopters provide access that would be impossible with other aircraft.
Okay, so we've talked about what makes helicopters unique and their diverse applications. Now, let's get into the heart of how these things actually fly. Let's talk about the rotor system.
The rotor system is where the magic happens. It's essentially a set of spinning wings, those blades, that generate the lift that keeps the helicopter in the air. And it's more than just the main rotors. We also have tail rotors, which counteract the torque of the main rotors, and tilt rotors, which can change their orientation to provide both lift and thrust.
So it's a pretty complex system. What are the basic components? We see a diagram here, Figure 1.4, that shows the mast, the hub, and the blades.
Right, those are the core elements. The mast is that central shaft that the blades are attached to, and it's driven by the transmission. At the top of the mast is the hub, which is the connection point for the blades. And the way the blades are attached to the hub, how much freedom of movement they have, that's what differentiates the various types of main rotor systems.
And those are the semi-rigid, rigid, and fully articulated systems, right? These terms define how much the blades can move at the hub, influencing how responsive and maneuverable the helicopter is. For example, a fully articulated rotor allows each blade to flap up and down, lead and lag, and even feather independently, giving it a lot of flexibility.
Exactly. And our source material dives much deeper into these different types in Chapter 4. But before we get too lost in the weeds, let's revisit that whole torque thing. You mentioned it earlier, but can you explain what it is and how helicopters deal with it?
Sure. So when those main rotors are spinning, they're creating lift, but they're also creating a twisting force, a torque, that makes the helicopter want to spin in the opposite direction. Imagine what happens if you try to spin a top. It stays upright because of the force pushing back against the spinning motion. Helicopters need a way to counteract that twisting force, or they just spin uncontrollably.
It's Newton's third law in action. For every action, there's an equal and opposite reaction, and that's where the tail rotor comes in, right?
Most of the time, yes. The tail rotor provides a horizontal thrust that counteracts the torque from the main rotor, keeping the helicopter pointing in the right direction. But there are other innovative solutions too, like the fenestron, a type of shrouded tail rotor, and the notar system, which uses a directed jet of air.
Right, there's no one-size-fits-all solution. And again, Chapter 4 in our source material explores those anti-torque systems in more detail. But let's talk about something else that's pretty interesting. The different rotor configurations. We see a lot of variety out there, don't we? And it's always fascinating to see how engineers have tackled those fundamental challenges of helicopter flight in different ways, whether it's about boosting lift capacity, minimizing vibration, or finding ways to simplify the control systems. Each design represents a unique approach.
We're all familiar with that classic single main rotor with a tail rotor setup. That's the one Sikorsky pioneered. But there are others, like tandem rotors.
Tandem rotor helicopters, like the one shown in Figure 1 to 6, have two main rotors, one at the front and one at the back, and they rotate in opposite directions. This cancels out the torque without needing a tail rotor, and it means all the engine power can go towards lift.
So they can really haul some serious weight. What about coaxial rotors?
Coaxial rotors, as seen in Figure 1 to 7, are a bit different. They still have two rotors spinning in opposite directions, but they're mounted on the same mast, one above the other. You'll often see this design in helicopters made by the Russian Komov Design Bureau.
Coaxial rotors, tandem rotors. It's like an alphabet soup of rotor configurations. And then there's the intermeshing rotor system.
Ah, yes, the syncropter. Illustrated in Figure 1 to 8, this system uses two rotors on tilted masts, with the blades actually intermeshing as they spin. No tail rotor needed here either, and they're known for their stability and high lift capacity.
So we've got all these different ways to get those rotors spinning and lifting the helicopter into the air. But how does the pilot actually control this intricate machine? There must be a lot going on in that cockpit.
You're telling me. There are four primary controls: the cyclic, the collective, the anti-torque pedals, and the throttle. Each one plays a crucial role in managing the helicopter's movement and flight characteristics.
Okay, so let's break those down one by one. First up, the cyclic. What does that do? I think it's helpful to imagine tilting a plate as it spins. The cyclic allows the pilot to subtly adjust the angle of each blade as it rotates, which creates more lift on one side of the spinning rotor disc than the other. This effectively tilts the entire rotor disc, pulling the helicopter in that direction.
That's a great analogy. The cyclic, usually located between the pilot's legs, though some helicopters have different setups, allows the pilot to change the pitch of the main rotor blades throughout each rotation. This creates unequal lift across the rotor disc, causing it to tilt, and that tilt directs the helicopter's movement, forward, backward, and side to side. Figure 110 shows how this pitch variation works.
Okay, so cyclic for directional control. What about the collective?
The collective, often found on the left side of the pilot's seat, is all about controlling the overall lift. Unlike the cyclic, which changes pitch cyclically, the collective changes the pitch of all the main rotor blades simultaneously. Pulling up on the collective increases the pitch of all the blades, generating more lift and causing the helicopter to climb or accelerate. Lowering the collective reduces lift, causing it to descend or slow down. And figure 111 shows how the throttle control is often integrated into the collective.
So collective for lift and vertical movement, cyclic for horizontal movement. Got it. What about those pedals?
The anti-torque pedals, located where you'd find rudder pedals in an airplane, control the helicopter's yaw, which is the rotation around its vertical axis. Pressing on a pedal changes the pitch of the tail rotor blades, altering the amount of thrust it produces. This allows the pilot to turn the helicopter's nose left or right.
And lastly, we have the throttle. What does that do?
The throttle, as you might expect, controls the engine power, which ultimately drives those rotors. Helicopters need to maintain a very specific rotor speed, measured in revolutions per minute, or RPM, to stay in the air and maintain control. The throttle allows the pilot to adjust the engine power to keep those rotors spinning at just the right speed. In single-engine helicopters, you'll often find the throttle as a twist grip on the collective, though some systems are automated. Multi-engine helicopters typically have a separate lever or switch for each engine.
It sounds like a lot to manage, but it's all about coordination, right?
Exactly.
Yeah.
But there's more to it than just manipulating the controls. The pilot also needs to understand the different flight conditions and how the helicopter behaves in each of them. And our source material highlights two basic flight conditions: hovering and forward flight.
Hovering, it seems like it should be easy. Just stay still in the air, right?
It's actually one of the most challenging aspects of helicopter flight. When a helicopter hovers, it's essentially creating its own wind, a turbulent downwash from the rotors, and that can make things pretty unstable.
So it's a constant battle against the forces you're creating.
Precisely. The pilot has to constantly make adjustments, using the cyclic to counteract any drift, the collective to maintain altitude, and the pedals to keep the nose pointing in the right direction. It's a delicate balancing act.
And how does forward flight differ?
Well, when the helicopter moves forward, the airflow over the rotors changes, and that affects how the controls respond. Initially, pushing the cyclic forward causes the nose to pitch down, which increases airspeed, but also can lead to a loss of altitude. Pulling back on the cyclic has the opposite effect. But here's something interesting. Once the helicopter reaches a stable forward flight condition, the horizontal stabilizer, which you can see in figure 112, comes into play. Now, unlike in airplanes where the horizontal stabilizer mainly provides lift, in a helicopter, its primary role is to keep the aircraft level and minimize drag, so you don't need as much constant input from the cyclic to maintain pitch.
So the horizontal stabilizer in a helicopter is more about stability than lift. Got it.
Exactly. To climb or descend while maintaining airspeed, the pilot primarily adjusts the collective. Increasing collective pitch results in a climb, and decreasing it causes a descent. And to change airspeed while maintaining altitude, you need to coordinate the cyclic and the collective. For example, to speed up at a constant altitude, you'd lower the collective slightly while pushing the cyclic forward. And just like in hovering, those anti-torque pedals are crucial for keeping the helicopter balanced during turns, making sure it's not slipping or skidding through the air.
So much to think about. But it all boils down to understanding those core principles of lift, thrust, and control, and how they're manipulated through those four primary controls. And then, of course, there's the added complexity of managing the helicopter in different flight conditions.
It's a testament to human ingenuity that we've managed to design and build machines capable of such complex and demanding flight.
Absolutely. So as we wrap up our deep dive into the fascinating world of helicopters, what are the key takeaways we should leave with?
We've learned that helicopters are unique aircraft that generate lift using rotating wings, enabling them to take off and land vertically and hover in place. We've seen how their development was driven by key innovations in engine technology, particularly the advent of lightweight turboshaft engines. And we've explored the incredible versatility of helicopters, how they're used in everything from search and rescue to construction to transportation, and so much more.
And by understanding those primary flight controls, the cyclic, the collective, the anti-torque pedals, and the throttle, we've gained a glimpse into the complex world of helicopter piloting.
It's been a fascinating journey, and I hope our listeners have gained a deeper appreciation for these remarkable machines.
Absolutely. Now, as a final thought, it's worth considering the future of rotary wing aircraft. With all the advancements we've seen, what exciting new possibilities might be on the horizon.
Imagine a world where personal air mobility becomes commonplace, where helicopters or their futuristic equivalents are used for everyday transportation. Or think about the potential for even more advanced logistical operations, delivering goods and services to remote or hard-to-reach areas with even greater efficiency.
The possibilities are truly endless, and as technology continues to evolve, I'm sure we'll see even more innovative and transformative applications of these incredible flying machines. Thanks for joining us on this deep dive into the world of helicopters.
My pleasure. Always a thrill to talk about these amazing machines.